So this is what we want. We want to create the output directory, grab all file names in a directory, filter them according to their extensions, process text files, copy other files without modification, parse each text file, build an index of the result, convert the files to HTML, and write everything to the target directory. Note that we didn't write this code immediately in the final form it was presented. This was an iterative process of writing code, refactoring, splitting functions, changing type signatures, and more. When solving a coding problem, we can start small and simple, do the things that work, and refactor it when it makes sense, and make the code clearer and more modular. In Haskell, we pride ourselves in our ability to refactor code and improve it over time. And that principle holds when writing new software as well. We're going to create a new module, and we'll use the directory and file path libraries to manipulate directories, files, and file paths. We'll use the new abstractions we've learned, such as traversable and monad, and the concepts and types we learned about, either, IO, and exceptions. Let's create a new module, hsblock directory, which will be responsible for handling directories and multiple files. From this module, we'll export the convert directory and build index functions we've defined before. We're gonna be doing a lot of things, so for all that, we'll need quite a few imports. Some stuff we wrote for ourselves, some Haskell functions, some IO, and so on. If you are not sure what a specific function we're using does, you can look it up on Google, read the type signature and the documentation, and play around with it in GHCI. We can start by describing the high-level function convert directory, which encapsulates many smaller functions, each responsible for doing a specific thing. Content directory is quite imperative looking. It looks like a different way to describe the steps of completing our task. Here we trust that each IO function handles errors responsibly and terminates the projects when necessary. Let's examine and implement each step in order. First function is get directory files and content. We can represent it using custom data type, which has two fields. First one with file paths and their content, and second one with other file paths that has to be copied directly. This function is responsible for providing the relevant files for processing, both the ones we need to convert to markup and their textual context, and other files we might want to copy as is, such as images and style sheets. The function does four important things. List all the files in the directory. Split the files into two groups according to the file extension. This is done with the partition function. First group is text files, second group is other files. Third, it reads the contents of the txt files and reports when files fail to be read. We're gonna look at it later. And at the end, we return the result with the data type we just defined and reviewed. So this third part about reading the content is the most involved, so let's explore it even more. Apply IO on a list has the following type signature. It tries to apply an IO function on a list of values and documents successes and failures. This is a higher order function which should apply particular IO function, like a read file, for example, on a list of things. In our case, it's file paths. So what do we do for each thing? It returns the thing itself along with the result of applying the IO function as an either, where the left side is a string representation of an error if one occurred. And notice how much the type of the function tells us about what it might do. Because the types are polymorphic, there is nothing else to do with the A other than apply them to the function. And we cannot just get B out of nowhere. We can only get it from the result of the function. This function uses exceptions to catch any errors that might be thrown and encodes both the failure and success cases in the type system using either, delaying the handling of exceptions to the function caller while making sure it's not going to be forgotten. Let's take a look at the functions that handle the errors by reporting them and then filtering out all the cases that fail. Filter and report failures has the following type signature. It filters out unsuccessful operations on files and reports error to the standard error. This code may seem a bit surprising. How come we can use foldMap here? Here's a reminder of a foldMap function. If we specialize this function for our use case, substituting the general type with the types we are using, we learned that we have IO of a list of tuples is a monoid. And indeed, list of A is a monoid for any A with an empty list as mempty and concatenation as a mapend operation. But also IO of A is a monoid for any A that is itself a monoid with pure mempty as mempty and lifting the append as an append. Using these instances, we can map over the content, handle errors, and return an empty list to filter out a failed case or a singleton list to keep the results. And the fold in foldMap will concatenate the resultant list where we return all of the successful cases. These functions are responsible for fetching the right information. Next, let's look at the code for creating a new directory. Create output directory or exit itself is not terribly exciting. It does what it's named. It tries to create the output directory and exit the program in case it didn't succeed. Create output directory is a function that actually does the heavy lifting. It checks if the directory already exists and checks if the user would like to override it. We've seen this before. If they do, we remove it and create the new directory. If they don't, we do nothing and report their decision. In this part of code, we convert files to markup and change their input file paths to their respective output file paths, meaning we go from txt to HTML. We then build the index page and convert everything to HTML. We can implement this by splitting this into smaller functions. First, we would need to convert it to markup file. We need to convert each text file into the output markup file. We can do this using map. Then we should build an index out of these files, and so it matches all the other files. We put it together with its file path, which is index.html. Next, we have to convert all the markup documents or files to the HTML, and then together with the index, render all of this as a HTML. To output markup file, takes a file and the content, parses the content, takes the base of the name, which means it just drops txt, and adds the HTML to it. And the convert file converts the file and keeps the file path as it was. And last, render file, which keeps the file path but renders the HTML and returns a string. Notice that we modify the second element of a tuple, which could be done with the fmap thanks to the functor instance, like it's done in the book. I didn't do it here to keep it simple. The only thing left to do is to write the directory content after the processing is completed to the newly created directory. Here we use apply IO on list again to do something a bit more complicated. Instead of reading from a file, it copies from the input path to a newly generated output path. Then we pass the result, which has the type list of tuples of a file path and either string or unit, to filter and report failures, to print the errors and filter out the unsuccessful copies. Because we're not really interested in the output of filter and report failures. We discard it with void, which returns the unit as a result instead. And write files, it does what it says. It writes file to directory, recording errors to standard error. This code looks almost exactly like copy files, but the types are a bit different. Haskell's combination of parametric polymorphism plus type classes for abstractions is really powerful and has helped us reduce quite a bit of code. This pattern of using apply IO on list and then filter and report failures happens more than once. It might be a good candidate for refactoring it. Depending on your preferences, the resulting code is either easier or more difficult to understand. And with that, we have completed our hsblock directory module, which is responsible for converting a directory safely. Note that the code could probably be simplified quite a bit if we were fine with errors crashing the entire program altogether. But sometimes this is the price we pay for robustness. It's up to you to choose what you can live with and what not. We hope that this saga has taught you how to approach error handling in Haskell in case you need to. Let's recount the things we've learned recently. We discussed several ways to handle errors in Haskell: encoding errors as a data type and using the either type to encode a value on error, which is a useful approach for uneffectful code. We learned about using except when we want to combine the approach in the first one with either on top of an existing type with monadic capabilities. Learn how to use exceptions in IO code. We've also learned a new abstractions and techniques. The traversable type class for data structures that can be traversed from left to right, such as linked list, binary trees, and maps, pretty useful when combining with another applicative functor like either or IO. The monad type class extends the applicative type class with a join operation or function. We learned that either implements this type class and so does IO, and the monad trans type class for monad transformers for types that take other monads as inputs and provide a monadic interface like using bind and do notation, etc., while combining both their capabilities. We saw how to stack an either like monad transformer except on top of IO. We're almost done, only a couple more things left to do with this project.